So the last section we're going to talk about in this chapter is 2.7 linear models. In the linear models, book talks about several things, but we're going to talk about only two for this class, growth and decay, and then Newton's law of cooling and warming. You are given growth and decay linear model as dx over dt equals to kx. And you will be given initial value, the x t naught equals to x naught. So let's work on this. So a culture initially has p sub 0 number of bacteria. At t equals to 1 hour, the number of bacteria is measured to be 3 over 2 times p naught. So p naught is the initial one, and 1 hour later, we have 3 over 2 times p naught number of bacteria. If the rate of growth is proportional to the number of bacteria p of t present at time t, determine the time necessary for the number of bacteria is to be tripled. So based on this kind of information, we can say we have initial p naught. Okay? So init is going to be p naught, or sometimes we can call it this p naught. And then when p of 1, it is what? 3 over 2 p naught. Okay? And then the question is to what? So basically ask us to find the p, right? When we have 3 times of p naught. And growth and decay model is that dx over dt equals kx. So since this problem using p as a variable, we can say dp over dt equals to k times. And then I'm going to move kp to the left-hand side, then dp over dt minus kp equals to 0. It is a linear model, so integrating factor is going to be e to the integral negative k dt. So that is e to the negative kt. So we're going to multiply integrating factor to all the terms. We have dp over dt times e to the negative kt minus kp times e to the negative kt equals 0. And then left-hand side, gonna be d over dt, p times e to the negative kt. And the right-hand side is 0. We're good. Now we're gonna take the integral for both sides. Then the left-hand side is gonna be just p times e to the negative kt. Right-hand side is gonna c. And we're gonna multiply e to the positive kt, then we have p equals c e to the kt. So for the linear model, growth and decay, you don't have to go through these steps every time you solve the problem. This is the first time and the last time you're going to do that. You can just simply use this starting from here. You have a linear model problem, then you're going to let p equals to c times e to the kt, or r equals to r times e to the kt. I mean, it depends on the variable you are given. You can use all of those. And basically, c is the c naught. And this is the same as p equals to p naught e to the kt. When you solve the differential equation, we always use the initial condition to find the c. Now, we have one relationship up there saying P1 equals 3 over 2 P naught. So we're going to use this initial condition to find the value of K first. Okay. So P1 equals, I'm going to write this one. P of 1 equals 3 over 2 P naught that equals P naught e to the k times 1. This time is T in here. T equals to 1. Then P naught will cancel out. And then we have a 3 over 2 equals e to the k. Take ln 3 over 2, 0.4055 equals, this portion is going to be k. So now our new equation P of t equals P naught e to the 0.40. Now we need to find t for 3P naught, right? So P of t equals 3 times of P naught equals P naught e to the 0.406 t. These two cancel out. Then we have 3 equals e 0.406 t. Take the ln for both sides. Ln 3 equals 0.406 t. And you use your calculator, you can find the value of t. Okay, so let's work on problem 2.7.6. So initially, 100 milligrams of radioactive substance was present. So radioactive R, initial value R of 0 equals to 100. After 6 hours, the mass had decreased by 3%. 6 hours, R of 6 equals original times 1 minus 0.03, and then that's 0.97, so basically 97 milligrams. If the rate of decay is proportional to the amount of the substance present at time t, find the amount remaining after 24 hours. Just to find R24. So start with R of t equals I sub 0 e to the kt, and we know I sub 0, which is 100, and we can find k using R6 equals to 97. So R of 6 equals 100 e to the 6k, that is 97. And then you divide both sides by 100. So E6k equals to 97 over 100. Take the ln for both sides. Then we have 6k for the left-hand side, right-hand side, ln 97 over 100. From there, and R of t equals 100 e to the negative 0.005 t. They want us to find 24 hours later, right? So t equals to 24 now. So R24 equals 100 e to the negative 0.005, 24, and use your calculator, 0.53 milligram. Any questions? So we just did problem 2.7.6 and then 2.7.7. Using the previous problem, find the half-life of that substance. So R of t equals to 100 e to the negative 0.005 t. That's what we had as the linear model. This time, this is the initial substance as 100 milligrams. Now half-life, that means this is half of this. Okay, so we're gonna have 50 equals 100 e to the negative 0.005 t. So 1 over 2 equals e to the negative 0.005 t. Take the ln 1 over 2 equals to negative 0.005 t, and use your calculator, equals about 1:38, 6 hours. Any questions? Okay. The next one is Newton's law of cooling or warming. It can be modeled as a dt over dt equals to k t minus tm. For this is the only difference, tm. And then tm is the ambient temperature. So in the description of the problem, you're going to have an initial temperature. And it could go up later, it could go down later, depends on the problem, but you'll get the initial temperature. So we need to have that initial temperature. Right? So when a cake is removed from the oven, its temperature is measured at 300 Fahrenheit. 3 minutes later, its temperature is 200 Fahrenheit. How long will it take for the cake to cool up to a room temperature of 70? So we have d big D dt equals to K big T minus the room temperature is a 70. Let's distribute K big T minus 70K. Then I'm going to move KT to the left-hand side. Then we have d big T, the T minus KT equals to negative 70K. It's a linear, right? So integrating factor is going to be e to the integral negative k dt. So that is e to the negative kt. Now we're going to multiply this integrating factor to every single term. dt over dt times e to the negative kt minus kt times e to the equals to negative 70k. And then left-hand side, e over dt t times e to the right-hand side. We good? Okay. Now we need to take the integral. We have big T times e equals negative 70k integral dt. Take the integral of that 1 over negative k e to the negative k t plus c. And k cancel out, negative cancel out, 70 e negative k t plus c. We multiply e to the kt for the equation. Then we have a t equals 70 plus c e to the kt. Same thing for the linear model. If you are asked to find the temperature using the Newton's equation for the finding temperature after a certain period of time, then you don't have to go through these steps. This is the first and last time I'm showing you. You can start from here. So whatever the temperature you will be given, you can just add that one. And then we already knew this is the C times e to the kt. That's the model that we already saw from the previous example. I mean, this is not the only way. By looking at this, let's do this. dt d big T over dt equals k t minus 70. If you multiply dt for both sides, we have a dt equals to k t minus 70 dt. Divide both sides by big t minus 70. 1 over big T minus 70 dt equals to k dt is a separable. That's a 2.2. So if you use technique with the separable, it is separable. Now we take the integral for both sides. We have ln t minus 70 equals, this is k t plus c. Take e for both sides. Then we have t minus 70 equals e to the kt times e to the c. Then t equals 70 plus e to the kt c1 kt. So we end up getting the same answer. So it's a kind of good review for separable. They want us to find t of t equals to 70 And then initial condition T naught is 300, and initial condition T of 3 equals 200. Okay, so T naught equals to 300, so plug it in. When T equals to 0, this is the case, then it's going to be 1, therefore C1, 230. So our new equation is now 70 plus 230 e to the k. Now using the second condition T3, we can find the value of k. T of 3 equals to 200 equals to 70 plus 230 e to the k3, which is 3k. So 200 minus 70, 130 over 230 equals 3k. ln 130 over 230 equals 3k. And then using your calculator, k. So the complete equation 70 plus 230 e to the negative 0.t. And they want us to find the final temperature is 70. They say impossible. So if we plot this, looks like this. So start going down from high temperature, but eventually we're gonna reach to close, very close to room temperature 70, but it's based on this model, it's not gonna be exact 70 forever. Okay, we good? Yeah, let's work on problem 2.7.16. A thermometer is taken from an inside room to outside, where the air temperature is 5 degrees Fahrenheit. After 1 minute, 1 minute later, the temperature is 55. After 5 minutes, now it's reading 30. What is the initial temperature of the inside the room? So air temperature is 5. So we can say T equals 5 plus T initial e to the kt. If T1 is 55, and that is 50 equals to T naught e to the k. The second condition, T5 equals to 30, that equals to 5 plus T naught e to the 5k. Now it's going to be 25 equals T naught 5k. So now we have two equations and two unknown, T naught and k. So let's use first equation to find T naught equals 50 over e to the k, and then plug this into the second equation. Then 25 equals 50 over ek times e to the 5k. 25 over 50 equals e to the negative k, e to the 5k. So 1 over 2 equals 4k. We take the ln equals, and then we can plug this k value into either of those two equations. 25 negative 7, 25 times 7. So finally, we have T of T equals 5T naught, 5 plus 17 T naught equals 5 plus 64.3 Fahrenheit.